Hi everyone. So thanks for joining today and sorry for any inconvenience for the schedule change. So today is April 26th, Thursday, April 26th, and we will be releasing a new module tonight. And you should all be working on your final projects as well and start gearing up to start studying for the final exam as well. So you'll have Today is the 26th, so tonight we're going to be releasing the inferences for correlation and single linear regression module. So this will be your final module with new material, and then next week will be a course review. So that will cover all of the material that you'll have to know for the final exam, and will be a review of all the material that we've covered. So, and your final project will be due next week on May 3rd. And the following week will be the final exam. So we'll be releasing the practice exam next week. So just like you had the practice midterm, you'll also have a practice final exam. And it'll be very similar to like when you took the practice midterm and the midterm. It's very, very, very similar. So for you guys who are in the session, would you like to go over some of the material that we've learned in this module, or would you prefer to talk about final projects, or we can do a mixture of both? I'm here to help answer any questions that you guys have and try to clarify anything that there might be misunderstandings about. Does anyone have any questions about the material, about their projects, about the course? So we have a question about the final project. Students confused about what we're supposed to be aiming for. So if you go on the course website under the Files tab, there's a document called Final Project Guidelines. So if you take a look at this document, this will be a good starting point, a good resource to take a look at to see what we're looking for the final project. So this gives you an overview and some guidelines for what you should be aiming for. And it'll also show you our grading rubric on the bottom. So it shows you exactly what we're looking for what we consider to be an A paper, a B paper, a C paper, and so on. So, just to go over, first, depending if you're an undergrad or a graduate student, you'll have a different page length. And the whole idea of this project is we're having you apply what you've learned in the class. So you're basically emulating what an academic or a statistician would be doing, is taking a data set, coming up with a research question, and then running statistical analyses to test whether you have enough evidence to support a conclusion based on your research question or not. So the whole idea is you're basically doing what's done in academia, what all these academics are doing with published paper, with peer-reviewed papers. This is more of an abbreviated format, and more of a simple format. So it's a nice exercise, and it shows you what's done in academia typically. So first of all, the paper will be 5 pages for undergrads or 10 pages for graduate students, double spaced, including all your figures and including your tables and graphs. And for the data set, you can use any of the data sets. Yeah, so for the research question, that's pretty much where you'll start. Is first you'll find which data set you want to use, and you'll come up with a research question. So they pretty much, in this case, they're pretty much going to go together. So first of all, let's talk on the data set for a second. You could use any data set that you want. We provide you a number of data sets in the class that you've already worked on for the problem sets throughout each week. So you're more than welcome to use any of those that we provide for you. For instance, even from the first week, we gave you the Titanic data set, and each week after that, we gave you a different data set. So, I've seen papers in the past where students have looked at the Titanic data set and they came up with a research question to see who was more likely to survive the Titanic. Was it, and looking at different demographics, looking at men, women, young, old, rich, poor, and try to come up with some kind of a question, and they ran analyses from that to come up with a conclusion based on the probability of someone being, a rich man. How likely were they to survive the Titanic compared to being a poor woman, for instance? So the whole idea is, first, I would say, try to look through the data sets and try to open the data sets, see what they look like, see what kind of variables there are, and see if you have any questions that you have about this data set and that you would be interested in doing some analysis on. So, what's nice is we give you a bunch of different data sets, and there's a number of different questions that people can come up with for each of the given data sets, and they're all very interesting data sets. So the whole point of the research question is, with academics, with the scientific method, the whole idea is we first come up with a hypothesis, a research question, and then after we make our hypothesis, then we run our analyses to see if there's evidence to support that hypothesis. And if there is, then you can conclude that you can make some kind of conclusion and discussion that will be an interesting finding for the field at large. So basically, you're gonna pick your data set, you're gonna come up with a research question, and you're gonna conduct your analyses. So you're gonna basically be performing what you've been learning throughout the course. You're gonna pick a few different statistical analyses. You're gonna run those analyses, and then you're gonna include your results section, which will be the results of your analysis. And then finally, you'll have a conclusion, which will be the discussion section about the significance of your findings and why this is important, why your results are significant. And yeah, so I mean, it's fairly straightforward. You can have different sections here, which we outlined here. You can have your abstract, introduction, data and methods, which will outline your data set and the methods you took to come up with your data. come up with your results rather. And then you'll have your results section, which will include the results of your analysis, and a conclusion section. And we give you in these two folders a number of different sample papers. So it's a great resource to be able to use to take a look at what we're looking for. So you can take a look at, there's, you can see here, there's 6 graduate papers that we provide for you. So you could take a look at each of them and get an idea of what we're looking for. So this paper talks about BMI and whether it's an accurate predictor of body fat. So they looked at one of the data sets that we provided for you, the student did, which was the body fat data set. So this was included in the regression lecture, if I'm recalling correctly. And you can see here, it's organized. They have an introduction, giving you a little bit of background on the field and the question in general. Then the data and method section. So the student talks about the data set and the variables and how they went about performing their analysis. And then the result section. So the student took a look at a regression model between BMI and body fat, plotted a linear regression model on a scatter plot here with those 2 variables, and talked about the regression model output, and then ran a correlation coefficient hypothesis test to see if this was if BMI was a good predictor for body fat, and finally made a conclusion based on those results. So as you can see, it's fairly straightforward. You're going to come up with a research question. You're going to use a data set, either one that we provide or one that you found on your own. And then you're going to run some statistical analysis to answer your research question. So the research question for this paper is BMI an accurate predictor of body fat, right? And the way the student went about answering it was to take a look at a scatter plot. So here you can see the student used R to make a scatter plot between BMI and body fat and a linear regression model. So as you can see here, even just from the figure, there's a positive linear relationship between the 2 variables, and it's a moderately strong relationship. The correlation was calculated to be 0.73, so student says it's very strong. And they included the regression output here. So the student says that it is a good fit for the data set. And finally, they ran a hypothesis test to see whether the correlation in the population is 0 or not 0, and the result was they rejected the null hypothesis, concluding that there is a linear relationship between the 2 variables. So the student concludes that BMI is a good predictor for body fat. But they also go on in the conclusion to write that it's not a perfect indicator. There's residual error and considering some other factors and limitations of the study. So that's definitely a good point, because yeah, I mean, it certainly there is a relationship here, but actually BMI is not the best predictor of body fat, because someone who has a lot of muscle would have a high BMI, but they might not necessarily have a high body fat percentage. And yeah, so you can look through all these different papers, and since the project will be due next week, I think it's definitely a good time to start, you definitely want to start finding your project, finding your data set, thinking about your research question, and there's plenty of resources on the discussion forum as well, both to ask questions or to get guidance on the final project. So if you go to the discussion forums, you can go to, so there's a few different posts here. So Nate made a post on finding a data set. So he listed a few different repositories for a good place to find different data sets for your project that you might want to look for your own. Of course, you can use any of the data sets that we've given you. So you can find those in the files section. If you just go to each of these different tabs, you'll see there's Titanic.R data. And what's nice about these data sets is they're already pre-cleaned and you're already familiar with them, and they're already in an R data format. So it might definitely be easier to use one of these data sets that we already give to you. So just to find a research question, to come up with a research question about one of these data sets that we've already given to you, as opposed to looking for your own data set, having to learn it, and then making sure that the data set has been cleaned and it's in the right formatting. So you can either use one of these data sets, and we've given you one each and every week for each different module, or otherwise you can look for your own, and we give you some resources on how to do that. So you can go to the discussion forum, you can go to this thread, and we give you a whole list of different resources. So there's the Harvard Dataverse repository. So this is a Harvard website which has data sets from studies that were conducted at Harvard. And you can see here, we also give you a number of different other data sets as well. In addition, the Mosaic package actually has a number of data sets loaded inside R as well that you can take a look at. So we give you a number of different resources if you wanted to look for your own data set. So in addition to this thread, we also have another thread for questions, concerns, and thoughts about the final project. So, this is a good place to get feedback from your fellow classmates and the teaching staff about the final project. So if you have any questions on that, this is a good place to post it and get some feedback on the final project. So someone had a question about a question on the mission for this week. So let's take a look at that. And then we also had a question about the chi-squared, goodness of fit, and test for independence. So So for the goodness of the chi-squared goodness of fit is we're looking at whether there is we're looking at expectations of a given distribution amongst categorical variables compared to what we actually observe. So just to give you an example, this example is using religious affiliation to look at young people and questioning whether their affiliation for religion will be broken down between Protestants, Catholics, and no affiliation. And their claim is that it'll be a 60% split of Protestant, 35% Catholic, and 5% having no religious affiliation. This is looking at Americans aged 18 to 35. So here we have our sample set. Our sample size is 518. And for goodness of fit, our requirements to run a goodness of fit test is that first, that we have randomly selected data from a population. Second, that the sample data consists of counts for each of the different categories. And third, that the expected count will be at least 5. So the expected count for a category is the number of observations that would exist if the data actually have distribution that's being claimed, and there's no requirement for the observed counts for being at least 5, it's just the expected. Okay, so we said there was a sample size of 518, and we can look at the expectation breakdowns to come up with a contingency table. So this is what we actually observed. And what was claimed was there was a 60%, that our breakdowns were 60% Protestant, 35% Catholic, and 5% none. And this is what we actually observe here. So this is the observed counts. And then the expected counts, what we would do is we would just multiply the sample size by each of the different expected proportions to come up with an expected counts. And here we can see each of these are greater than 5, so it meets that requirement. So that means we can run a chi-squared goodness of fit test. And a chi-squared goodness of fit test is a hypothesis test. So just like all our other hypothesis tests, we're going to have 5 steps. We're going to state our hypotheses, select a significance level, we're going to compute the test statistic, and then we will either compare the test statistic with the critical value or look at the p-value and then make a conclusion. So our hypotheses for this chi-squared goodness of fit test will be that the proportions in each of the different categories is equal to what is observed. And the alternative is that at least one of them is not equal to what we actually observed. And to calculate the test statistic here, the formula for the chi-squared test statistic will be the summation of the expected minus the observed squared for each different one divided by the expected count. And then you're going to sum those all together to get a chi-square value. And that's the chi-square test statistic. So that will tell you how far away from the actual distribution of counts is the expected distribution of counts. So the more extreme the test statistic is, the more inconsistent the data is with the null hypothesis. And so it's good to know what the chi-squared is plotted on the chi-squared distribution, which will change shape depending on the number of degrees of freedom you have. And the degrees of freedom for a chi-square test will equal to k minus 1, where k is the number of categories, right? So in this past case, we had 3 categories, right? There was Protestant, Catholic, or no affiliation. So the degrees of freedom would be 2 in this case. So since there's degrees of freedom of 2, the chi-square distribution model will fit on this shape. So as you can see, how the chi-square distribution will change as you increase your degrees of freedom. It will change accordingly. And this is just all those different chi-square distributions plotted on the same axes. And then you'll compare the test statistic with the critical value and make a conclusion. So the critical value for degrees of freedom of 2 at a 5% alpha value will be about 6, right? So we could actually even calculate this by hand. Let's say. Okay. So here we said that we had, this is the table of observations, and we calculated what our expected counts are. So from here, we could just calculate what our chi-squared test statistic will be. And we said the way we would do that is we would take each of the expected values. So the first one, 310, we expected there to be 310.8 Protestants, but there's actually 247. So what we would do is take 310.8 minus 247 divided by 310, and then we have to square that, and then divide that by 310.8, right? And then we're going to add that to each of the different ones and come up with a chi-squared. So you should be able to do that. And we said that the critical value was about 6, right? So we can compare what the test statistic is with the critical value of 6 for degrees of freedom of 2. So if we do that, we take 310.8 minus 247 squared divided by 310.8 plus, and then we do it for each of the different categories. We sum that all together, we get 520.39, right? And we said that the critical value for a chi-squared distribution with degrees of freedom of 2 is equal to 6. So what does that mean? What do we conclude here? If we find that our test statistic is 520.4 and the critical value is 6, what will we do? So what should we conclude based on this information? Yeah, you got it, Michael. That's right. So you'll reject the null hypothesis that the expected proportions are equal to the observed proportions. Yeah, that's right. And you'll conclude with the alternate, which is that at least one of them is not the same, right? And that makes sense. And this is a very significant result, because 520 is a lot greater than 6, right? So in order for this, so this is a significant result. In order for it to be not significant, to conclude with the null, the chi-squared value would have to be less than 6. Okay. And the p-value is going to be really, really, really small. It's going to be basically 0, because this chi-squared value is all the way out here. So there's very little probability of getting a number higher than that. So this conclusion is that that scholar who thought that this was the proportion, we find that it's not the case, that young people are less religious than the scholar actually claimed, We could see that because he proposed that there was a 5% no religious affiliation, and we found that there was a lot higher than that. So that's what the goodness of fit test is. It's when you're looking at whether you have some kind of, when you have expectations of different categorical variables and you want to see if that's actually what's observed, that's when you're going to use a goodness of fit test. You're going to want to see if there's a fit to the trend that's being described, right? And then we can talk about a chi-squared test for independence. So this is it's another chi-squared test. It's using the chi-squared distribution, but it's not looking at goodness of fit. It's looking at whether you have independence or dependence. So let's take a look at that. So the chi-squared two-way test for independence we'll look at contingency tables again, and it will determine if the rows and columns are independent or dependent. So it's used when you have two categorical variables and the data has been gathered from a random sample from population. And the test statistic is the same as the one-way chi-square test, but the expected cell counts and the degrees of freedom are calculated differently. So this is a two-way test. Remember, the goodness of fit was a one-way test. So we could use this examples again with the religious affiliation. So looking at the same sample data set. And in this case, now we broke it down by gender. So now we have the religion amongst this different samples, 18 to 35-year-olds, Protestant, Catholic, or none, but we're also adding in a further subset. We're breaking down the gender between male and female. So now we have a 3x2 table. So before, remember, we just had the 3 categories. It was a 3x1 table. Now we have a 3x2 table. And the rows, right? It has 2 rows, females and male, and it has 3 columns, Protestant, Catholic, and none. And we said the total sample size was 518. And the question is, are the variables gender and religious affiliation independent or dependent, right? So what do you guys think? Do you think being male or female has any effect on what religion you are? What's your guess? What's your hypothesis? You think there is okay, so we have one person who thinks there is a relationship, another person thinks there is no relationship. So let's find out. So we're going to do a hypothesis test. So again, we have to state our null and our alternate hypothesis, select a significance level, and compute the test statistic, and then we'll make a conclusion, okay? So again, it's the same assumptions, right? We want to make sure that in each cell, we have at least 5 expected counts in order to do the chi-squared. So the hypotheses for the test of independence will be that the null hypothesis will say that in the population, the categorical variables are unrelated. That is to say that they're independent, right? And the alternate hypothesis will be that in the population, the 2 categorical variables are related. That is to say that they are dependent. And then we choose a significance level. So we'll be using 0.05 for alpha. And then we can compute the test statistic. So it's the same method of computing the test statistic. But first, we have to get the expected cell counts under the null hypothesis. And in order to do that with this test, we're going to use this formula. The expected cell counts is equal to the row total multiplied by the column total over the overall total. And this is how we're going to calculate our expected cell counts from the contingency table. So we can go through that together. And then we're going to compare it with the critical value, but just understand that also the degrees of freedom for this test is calculated differently. The degrees of freedom will be the number of rows minus 1 multiplied by the number of columns minus 1. So we said this was a 3x2 table. So if we take the number of rows, which was 2, and we subtract it by 1, we get 1. And if we take the number of columns, 3, subtract by 1, we get 2. So 2 times 1 is equal to 2. So we're dealing also, again, with a chi-squared distribution with degrees of freedom of 2. And we said before that our so it was similar to the previous example, but this is also a two-sided test. Okay. So let's take a look here. So this was our table of observations. So in order to calculate what the expected was, is remember, we have that formula. So we take the row total. So first, a good first step is when you have this data, if they don't give you the row totals and the column totals, you're going to want to sum all those up and put those in the margins, so it's easier to calculate. So here we could just total them up. 283 females, just by adding these up, we get 283. 235 males, we got that just by summing 104, 56, and 75 together. That equals 235. And then we also did the column totals, and this is the grand total, 518, the sample size. So in order to calculate the expected cell counts for each of the expected is we're going to take the row total, 283, multiplied by the column total. So the column total for Protestant, let's start over. So we want to find what the expected number of female Protestants are, right? So in order to do that, we're going to take the number of females, 283, multiply it by the number of Protestants, 247, divided by 518. Okay, and we get 135. So that's what we expect there to be. We expect there to be 135 female Protestants, and we observe actually 143 here. Okay, so we could try that with the next box. We could try this with female Catholics. How many female Catholics do we expect? Well, we would take 283 multiplied by 132 divided by 518, right? You can just get out your calculator. You can see what that would be. 283 multiplied by 76 divided by 132. And I got, sorry, not 76, times 132 divided by 518. And I got 72. So we expect there to be 72 female Catholics, and we observe 76. Do you guys want to try it? Try to calculate what do we expect? How many Catholic men? Or let's do this one. How many male atheists do we expect? Male with no religious affiliation. How many do we expect there to be? Try to calculate what we expect for this cell, where it says 75. That's the observed value. How many do we expect? Try to work that out on your own and come up with an answer. So Fatima says 63. Does everyone agree? $63. So 235 times 139 over 518, 63. Yeah, that's what I got. So hopefully everyone got 63. That's exactly right. So then you'll compute the test statistic, and it's done in the same manner as the previous test. We're going to take the expected minus the observation, squared divided by the expected, and then we get a test statistic. So here, our test statistic was 5.66, right? And our degrees of freedom we said is 2. And we're going to compare it with the critical value. And remember, we said that the critical value was 6, and our test statistic is 5.66, which is less than 6. So we will fail to reject the null hypothesis at the 5% significance level. So this means that we conclude with the null hypothesis, which says that religion and gender are independent, which makes sense because whether you're male or female should not have any relationship on what religious affiliation you are. So it's not like if you're male, you're more likely to be Catholic and females are more likely to be Protestant. So we failed to reject the null hypothesis that independence between gender and religious affiliation, and suggest there's no major religious differences between young men and young women. So that's the test for independence. So it's different. So they're different tests, right? So we use the test for independence if we want to see whether our variables are independent or dependent, and we can use this for contingency tables with many different rows and columns, right? And the goodness of fit test we're going to use to see if the observed values fit a given expectation. Okay, so they're 2 different tests, and they're run in 2 different ways. And so for the goodness of fit, the expected values will be given to you. Well, the expected proportions will be given to you, so you can calculate where your expected values are just from multiplying the proportions by the sample size. In this case, there's a different way of calculating the expected values by using that formula that we just went through. But aside from that, the chi-squared calculation will be the same, and everything else will be the same. It just your hypotheses test, your hypotheses will be different. The way of calculating the expected values will be different. The degrees of freedom will be different, and your conclusion will be different, because this is a test for independence, not a test for goodness of fit. So that's the difference between those 2 tests, and hopefully that helps clarify a little bit. And then there was another test that we covered in this lecture as well, called ANOVA. ANOVA, which is the one-way analysis of variance test. And just know the final exam will not cover ANOVA, but the whole idea of what ANOVA does is we have our test for means where we can use a t-test to compare 2 different means. But if we want to compare the means of like 3 different samples or 4 different samples, we would use ANOVA. And that's just a way to do that as opposed to running multiple t-tests. So this is a way you can use the analysis of variance test in order to take a look at the means of multiple different samples. So that's when you would use a ANOVA test. And I want to make sure I get to the other question about the mission, but just to understand what ANOVA is you're comparing more than 2 means. So you're looking at least 3 or more population means are equal. And it's going, and the ANOVA test will look at the different sample variances in order to conclude that. So your null hypothesis will be that the samples in 2 or more groups are drawn from populations with the same mean values, and the alternate hypothesis will be that the samples are not drawn from populations with the same mean values. So that's what your hypotheses will be. And then you'll run the ANOVA test and you'll conclude based on that. And if anyone wants to know more about the ANOVA test, I'm happy to discuss more about that. I just want to try to get to the other question about the question on the mission while we still have time, and then I can try to come back to the ANOVA test if people are still interested. Okay. So this is the mission. So we're working on the Wall Street data set for this week. So you had a question about question number 32. So this is looking at the data set. So first we're gonna have to work with R. So I'm just gonna download the data sets and I'll open up my RStudio so we can take a look at this. Okay. So we can take a look at the Wall Street data set. So we take a look at the different variables here. So we have gender, whether they rent a home or not, their social class, and then we have these different variables here. So this greedy is whether the respondent to the survey view Wall Street executives to be greedy or not. The community-minded variable will be whether they view Wall Street executives to be community-minded or not, and then intelligent, dishonest, and overpaid, and so on, right? And if we just look at the questions that you're referring to. So okay. So if you look back at so this is what the data set looks like, right? And then I'll just go back to the mission. So we see here that, remember from the data set, in the social class, there were three different categories. They put them in either the lower, the middle, or the upper social class for the respondent. And we are saying here, if you look at question 28, we're going to convert the contingency table between social class and dishonesty into a probability table. So we're going to create a table of unconditional probabilities, and we're going to call the probability of L to be the overall probability of being in the lower social class, and probability of D to be the overall probability of viewing Wall Street executives as being dishonest. and says treating the sample proportions as probabilities, what is the probability of L? So you'll use the R data set to calculate what the probability of being in the lower class is and the probability of being dishonest is. So these are unconditional probabilities. So you'll use the data set to calculate these probabilities. And then it's asking you to find the joint probability of the probability of D and L. And then it's asking you in the next question to find the probability of D times L, okay? And then the next question is saying, what do the results of the probability, what are the results of questions 28 to 31 suggest about the relationship between social class and dishonesty in our sample data? And it's, so the answers here are asking you whether it shows that they're dependent or independent or not. So if you remember back from the probability lecture, we said that if the probability of D and L is equal to the probability of D times L, that means that they are independent, right? And we said that if the probability of D times L is different than the probability of D and L, that means they are dependent, right? So once you've gone and calculated those different probabilities, it's straightforward to answer question 32 based on the calculations that you've calculated in the previous questions. Does that make sense? Okay, great. All right, so we've got about 5 minutes left. Does anyone else have any other quick questions? I'm going to have another session today from 3 to 4 p.m. So everyone's more than welcome to come back and join that one. Fatima has a question about a previous mission. Yeah. So which question do you have a question on? We can take a look at that. Yeah, you can. Okay. So we're going to look at mission 8, test for proportions. So which question should we look at? Okay. So in this module, we were looking at the science data set and looking at whether these different disciplines were believed to be scientific or not. So if we look at question 14, from the standard normal distribution module, we show that 95% of z-scores lie in the interval -1.96 to 1.96. What do we conclude regarding climate change using an alpha of 0.05? So what did you answer? Right. So let's go over that. So when do you reject the null hypothesis, and when do you not reject the null hypothesis? Yeah. So I mean, when we spoke about the um, so for hypothesis tests, we look at the test statistic, and we look at the critical value, right? And we compare the two. And if the test statistic is more extreme than the critical value, we reject the null hypothesis. If it is less extreme, so if it falls between the two critical values, we do not reject the null hypothesis. So, in this case, it's talking about a z interval for 95% z distribution. We have the two critical values of plus 1.96 and negative 1.96. So depending on what the test statistic was for this given test, if it falls in between those two values, so if it's any number that's greater than 1.96 but less than positive 1.96, you will not reject the null hypothesis. If it's any number greater than 1.96 or less than negative 1.96, you will reject the null hypothesis. So depending on what the answer was to the previous question, question number 13, this is saying that your p hat is 0.7. You want to test the hypothesis that the actual proportion is 0.65. And what is the test statistic? So you'd have to calculate that. But in any case, let's say it's 5.74. If it's 5.74, what will you do? If the z test statistic is 5.74, would you reject or not reject? Yeah, you'll reject it because it's greater than 1.96. So let's just go through and let's say whether we would reject or not reject for each of these. So 1.96, what would you do if it's 1.96? And this one's kind of tricky. Yeah, so it's right on the line. So technically that would give you a p-value of 0.05. So yeah, so it's right on the borderline. So I guess um, we say that if it's less than 0.05, you should reject it. So I mean, it's a tricky one. So I'd say if it was 1.96 exactly, that would be kind of borderline. But let's skip that one. We're not going to give you an example. It's going to be that tricky. 5.74, we said you reject it. What would you do for 3.41? Yeah, so 3.41, you would reject it, right? Because it's greater than 1.96. And what would you do for 1.28? Yeah, 1.28 you would fail to reject because it's in between negative 1.96 and positive 1.96. So you would fail to reject that one, right? So that's how that's how we do it with comparing the test statistic with the critical value. And the other method is by looking at the p-value compared to the alpha value. So we say if the p-value is less than the alpha value, we reject the null hypothesis. If the p-value is greater than then the alpha value, we do not reject the null hypothesis, right? So here we're using a 0.05 alpha value. So if we had a p-value of 0.03, you would reject the null hypothesis. If you had a p-value of 0.25, you would not reject the null hypothesis. Does that make sense? Yeah, so the two ways of concluding is you'll either look at you'll look at the test statistic compared to the critical value, which we just went over with the z. The other way of doing it is you can look at the p-value. You can look at the p-value compared to the alpha value. So if we have a p-value, which is the probability value, if that's less than 0.05, well, if the p-value is less than the alpha value, we reject the null hypothesis. If the p-value is greater than the alpha value, we do not reject the null hypothesis, right? So let's look at this question, question 24. This talks about the p-value. So let's look at this answer. The p-value is 0.01, so we reject the null hypothesis at 0.05. Does that make sense? Yes or no? Yes. Yeah, it makes sense because 0.01 is less than 0.05. Let's look at the next question. The next answer. The p-value is about 0.04, so we fail to reject the null at 0.05. Does that make sense or no? No, right? P-value is about 0.04, so we reject the null hypothesis at the alpha 0.05. What about this one? Yeah, that's fine. And this one, the p-value is about 0.05, so we fail to reject the null hypothesis at the alpha 0.04 level. What about this one? Yeah, that makes sense because 0.05 is greater than 0.04, so we do not reject the null hypothesis. So yeah, so that's the bit. That's how this works. So I think you understand it now, and you can just practice this. You know, a good way to practice it is you can do the mission over and see if you'll get all the questions that you got wrong correct now, just to make sure that you fully grasp the idea. You know, it's a good way to practice. All right, so hopefully that clarified things for you guys. I'll be back on at 3 o'clock, so you're more than welcome to come join that session as well. And good luck with the assignment tonight, and good luck with the final project as well. And let us know if you have any other questions. Okay, have a good day.